Welcome to the Dynamical Systems tutorial. So what's a dynamic system? So this term dynamics is a very general term that we use all the time in daily life, right? We talk about very dynamic person and the dynamics of political situation and things like that. And so in a lot of cases, we mean by that something varies in time. A dynamic situation would be something varying maybe rapidly in time. It's also this notion of somehow the range of variation in time. For instance, people talk about the dynamics of an audio piece, and I mean how loud versus how silent certain places are. The concept that daily life kind of concept that comes closest is really the one that's consistent with the word, the Greek word dynamis, which is about forces, and the notion of force, more abstract perhaps than physical force necessary, is something that causes time variation, so causes movement if it's a physical thing. So the account for time variation as coming from some underlying cause, a force, temporal, something like a force, a generalized kind of force. That's really what dynamics means, and maybe there is some intuition like that in the way people talk. It is, as a mathematical theory, it is maybe the most universal language of science and mathematical language of science. Across all different disciplines, you can really say that a lot of the mathematical formalization is using dynamical systems. There are probably only very few other branches of mathematics that have as broad and general applicability as dynamic systems. Of course, linear algebra and the structure of data and so on, that's important. And some optimality principles, cost functions, minimization, like in economics, that's often used. And stochastics, probability theory is another branch of mathematics that has a lot of application. But dynamical systems is certainly one of the major languages, and historically been probably the most decisive step in mathematics that impacted how we think about nature and about technical systems and so on. So it's very important. So it's useful if you understand the concepts of dynamics, then you can use that in a lot of different cases. So I know that all of you are supposed to know these sorts of things, but it's not always active if you don't really practice it. And so I'll just start with very elementary concepts, and then it will accelerate a lot. So we will get very far in just 2 hours. So hold on. So, when we're talking about time variation, then mathematically, that means that we measure the thing that varies, a variable, a state. Physics call this a state here by x, and then time variation means that the x depends on time. It's a function of time. Given a moment in time, there's a unique value of that function. So here, for instance, a variable could be the position that you have along a line, let's say along a long corridor where you're walking, and if you walk there, your position will change in time. And for instance, I'm suggesting changes linearly in time. Isn't that a deductive question I just asked? And the velocity with which you mean would be the rate of change of that variable, denoted here by dx by dt, so like a little distance in x divided by a little distance in time, and the distance here being infinitesimal. And then that would be velocity if it is position, and generally the rate of change. And so, for instance, here the case of walking at a constant velocity would lead to that linear increases of your position. So the slope of this function, when I plot the variable as a function of time, that is what the rate of change is, right? And the slope of a straight line is a constant velocity. Dynamical system really means that there is some systematic relationship between the rate of change of a variable and the variable's value. And I'm taking here this example. I have an exponential time course of this variable that I plotted here. And then if you look at its rate of change, you might know that here the rate of change is clearly negative, is decreasing, so it's a negative number. And here it's steeper than, let's say, here. So it's a more negative value. here at this round ball, it's not as steep, so it's a median value. Here it becomes flatter, so it's a smaller value, but they're all negative. And those who remember this from high school, the derivative of exponentials are also exponentials, and the negative, the decrease makes it a negative exponential. So these are these two time courses that we will look at. And now dynamical system being there is somehow a functional relationship between x dot and x, and we can guess it by plotting corresponding values. So like here, this little asterisk would be a high value of x, a very negative value of x dot. So it would be, here far to the right and far to the bottom, and then the full stop here, or the circle would both a little bit less negative or positive for x, and same for the square. And so if you plot this quantitatively, you will see it actually lies on a straight line. And that actually is now a dynamical system. It's a dynamical system because the rate of change is a function of x. It's also a function of time when we look at solution. But here, it's the function of time emerges from the relationship between the rate of change and x, and we would then therefore call this like a force. X dot here, as when it's expressed as a function of x, is a force-like thing. This is then what we call a dynamical system. And this is actually a linear dynamical system. And you see the time courses are exponential. So that answers the query that we did before this lecture started. You see why the answer is that exponential time courses belong to linear dynamical systems. And linear really means that the force, the rate of change here, is a linear function of x and not of time. And then time course is exponential. So linear differential equations are very important. So it's the joke that engineers only treat linear differential equations, and actually physics is very largely dictated by that, even though I'll come to that when you introduce nonlinearity. So it's very important, and we'll understand in a moment why it's so important. And this one differential equation that you should probably all know or be able to learn by, to solve is this linear differential equation. I've written down here. We often replace the dx by dt by a dot over the x. So this is the derivative of x by time. You might have learned x prime also as a derivative, and that's when just for x depending on any other kind of variable like x of y. When it's time, then the convention in physics is to put a dot here on top. Apparently, with some Leibniz proposed this notation, and Newton proposed that one, and we use it interchangeably these days. I typically use x dot. So here I put a tau here on the left. Tau times x dot equals minus x. I could just divide by tau, and then it would be the slope here. So 1 over tau would be the slope. I put the -1 here. So this here, if plotted this way, the slope is -1. If I divide by tau, the slope would be -1 over tau. And the solution of the differential equation is x of t is the initial value of x, x of 0, times the exponential of minus t divided by tau. That's why I put the tau explicitly to the left. I actually plotted this by hand, but it's supposed to be an exponential time course. You see, it's a little uneven here, the plot. So this is a exponential relaxation, as we sometimes say, relaxes to its ultimate value. That's our jargon for exponential decay. Here, the decay will be to 0 ultimately. You can see the exponential has very special properties that we'll talk about in a moment. For instance, if you insert the time tau, so here, this will be the time tau, then you would have that it's the state of x at time tau is equal x at the initial time times exponential of -1. Exponential, e is 2.7 something, the Euler number. So that to the power of -1 is 1 over e. So it's about 1/3, let's say 1 divided by 2.7. And so that will mean here that the distance here of x of 0 from the ultimate value, which will be 0, is reduced to about 1/3. So this should be here, this distance should be about 1/3 of that initial distance. Again, I did this by hand. This might not be perfectly true here. So that's the meaning of this tau. That's where this distance decreases by the factor e, and we call that time scale. And the critical idea of the time scale is that this characterization of the change is independent of the exact units in which you measure x, for instance, of the initial value. For instance, if I ask how the value at this time, x of 0 divided by e, how long it takes for this to be decreased by the same factor, namely again by e, then it takes the same amount of time. Just put in 2 tau here, then I have exponential minus 2, so that is 1 over e times 1 over e. Then you would have a further reduction by again to a third, and that takes the same amount of time. It's only the exponential that has that property. That's why it's so important, right? And sort of expressed here by this idea that the rate of change is proportional to x. That is, the closer you get to this terminal value, the smaller the rate of change, and therefore now you cover a smaller difference, but the same difference in percent of your previous distance. So this differential equation, this solution, you can check yourself that it's a solution by just taking the derivative. I will invite you to do that. Just have to know the chain rule and how to take derivatives of exponentials. That's the one equation that you should really know. And I'll say in a moment why it's enough to just check it. Why that's actually then really proving that it's the solution. Just to clarify that first, so a nonlinear dynamical system would be an equation where the rate of change is just some other function of the state and not a straight line. So it's not a very strong constraint to be nonlinear. It really just means not a straight line, right? There are many ways how that function could be something other than a straight line. Okay, now this is the core property of dynamical systems. That's the core idea. This is the idea that you really should try to understand. So when I said that dynamical systems are accounts for change, so for time courses, accounts in the sense that certain forces, some causes create the change. The concrete mathematical meaning of that is what mathematicians call the existence and uniqueness theorem. And it really says that if you have some initial value of your variable, you know that you're at some point, and you know this function, the rate of change as a function of the state variable, then you can predict the future. The future is uniquely determined in some sense. But and first, let's see intuitively what that means. For instance, here, if I know I'm initially have this value x, then you can do some kind of mental simulation where you say, okay, this means I have this rate of change. It's a negative rate of change, not very large. And therefore, the next moment I have a value that's a little bit to the left of this. Negative means decreases. So I have a smaller x, and then you can look it up again. So again, a negative value. And so you can sort of mentally integrate that to see that you're moving left here, if this is the dynamical system. And we'll be doing that a lot. So that's sort of the intuitive realization of this idea that the present determines the future. And so what's really deep about that is that it's that all that you need to know is the value of the dynamical system just at any moment in time, which I now call present. And then the entire future is determined. That is, you don't need to know the past, you don't need to know a whole history. It's enough to just know the present, one value. Some of you might know this concept in stochastics. So when you look at stochastic systems, and they're not deterministic, so it's not you cannot uniquely predict the future, but you can predict future probabilities. And then there's this analysis question, what do you need to know to make a prediction? Do you need to know the entire history of that system? Or is it enough to just know the probability distribution at some point? And the Markov property, the Markov processes, those are the dynamical systems like stochastic processes. Those are the processes where you only need to know the present at some point, and you don't need to know the past. So that's a core idea, that just knowing the state at some point determines the future. You can then actually turn that around and think about how many things do you need to know to predict the future. And that's harks back to this question about oscillations. I'll show you a concrete answer to that in a moment, but the key idea there is that in an oscillation, you would predict the future from just any point. And if you have a single variable, the future should be uniquely predicted by that. But in oscillation, you go up through a value and then you can return through a value. And these two different ways of going through the same value actually have different futures. And you need, in one case you go down, in the other case you go up, right? You need a second variable to characterize that difference. It's called sometimes the velocity, second order differential equation, or you have just a second variable. So you can use the uniqueness to sort of count how many variables you need for a dynamic system, how large the state space is, as we say. And if you can't predict the future, it could be very well because you haven't introduced all the variables that one needs to know to predict the future. So sometimes, something is a dynamic system. Let's say the brain could be a dynamic system, but that's not maybe so constraining as such because brain has maybe 10 to the power of 15 variables or more, and you would typically not know their state. And so the prediction of the future isn't really very powerful, even though philosophers have actually argued about things like that, like whether we have free will based on questioning, asking whether everything is just determined by the initial state. It's clearly a wild extrapolation from what we know empirically. So that's the core idea of dynamic systems. I just clarify, I have these slides here to define some terms that we're using all the time. So I already said this dynamical variable. When we talk about dynamical systems, we often talk about these as being state space, that X is the state, and that state is what changes. Just a term that we use. In physics, actually, sometimes this is called phase space for some historical reasons. I try to avoid that because it creates confusion with other uses of the word phase, but that's a synonym. And we often, this is sort of jargon in this field that we say, this function of the state that is the rate of change, we call that the dynamics of X. Mathematicians call this the vector field for reasons I'll point out later. And so this is just jargon. When we plot X dot versus X, that's plotting the dynamics. So this thing here would be the dynamics, but that's just jargon for this equation. And then, a time course that fulfills the equation is called the solution to the initial condition. So that means that its rate of change is in fact that function, and that its initial condition is the given initial condition. Right? That's just defining the terms. So yeah, we had so the example I plotted was when there was just one variable X, and then of course you can have many variables. I already hinted that you would have to find out how many you actually need to determine the future. So for instance, a vector valued dynamical system where X is the vector of n such variables would be called sometimes a system of differential equations. And oscillations, for instance, need at least two variables. And sometimes can be done with something called second order equation, which I'm not going to explain here. There are some other dynamic systems that I really only mentioned to make context. It's not like we use them here in this course. So for instance, many of you who have studied like physics, electrodynamics, Maxwell equations may know that they are so-called partial differential equations. In partial differential equations, the variables are actually themselves entire functions. So it's a generalization of this idea of vectors. If you have continuously many variables, so these are not discrete indices, but the index becomes a continuous variable. Like for every location in space, you have an electrical field or electrical potential. Then you get a differential equation where the variable depends not just on time, but also on these other variables. And then the right-hand side could depend also not just on the variable itself, x of yt, but also on some partial derivatives. So derivatives with respect to the space. You might remember the Maxwell equation has some gradients and Laplace equation, things like that. So a lot of physics stuff with so-called fields in physics are of this nature. The Schrödinger equation is of that nature. It's actually a linear differential equation. partial differential equation. There are also integral differential equations. They are essentially the same sort of thing, but except of the instead of having derivatives, you have integrals. So it depends on more than one value along that other spatial dimension there. I call that space now, this argument here. So that the rate of change depends not on a function of the variable x at that same y, but also at other locations y. And this is, for those of you who watched the winter semester, is of course what the neural field dynamics is like, right? These integrals are reflect couplings in neural networks. So neural networks in some abstract sense could be considered integral differential equations. In this semester, this will not be so much of a topic, so you don't need that. But if you listen to it in the winter semester, then you will be in this class, and there can be treated just the same way with the same concepts that we'll be just using for ordinary differential equations. So in these cases, the initial condition, the state that you have, are entire functions. You have an initial function of space, for instance, the electrical potential in the entire space as an initial value. Or in neural fields, it's the initial activation pattern in the brain, or corresponding neural population in the brain. A little bit different. These are delay differential equations. We stay away from them here in this course, but they are sometimes a little bit confusing because they seem to violate this idea of the present determines the future. So a simple delay differential equation would be one in which the rate of change depends on the value in the past, in like not the current value of t, but a t of some shifted by some delay. So this is sometimes used to describe neurons, in that so-called synaptic delay at the neuron makes that the input of a certain time later determines what earlier determines what happens now, let's say on the membrane of that neuron. Because in the synaptic gap, there would be some other processing that's not included in the model. In a more radical form of that, it would not depend just on one earlier time, but on continuously many earlier times. So an integral over time from maybe some values, could be some limit here, to the current time, and all the past values matter. So this would be that a whole piece of trajectory would matter. So you see, this sort of violates a little bit this idea of the present determining the future, because here you would say the past, or maybe a whole piece of history, determines the future. These are sort of, it's a part of mathematics, and mathematicians have tried to lift all the concepts from dynamical systems to these sometimes called functional differential equations or delay equations. They're not really certainly not good descriptions of most natural systems or physical systems, because you can see how would the past influence the present. There has to be some agent that does that. For instance, when engineers build filters like that, these sort of equations are sometimes used as filters. Then they have a computer that stores the past values, and through that storage only you can then actually compute how you're going to evolve in the future. And so so that's computationally. And in physical systems, like in the synapse example, right, the synapse is supposed to do a delay, but what it really means is there are some physical processes that you just haven't included in your model of these vesicles going, from the across the so-called synaptic cleft, actually, that diffuse across, and there's some time involved in that, and it's just the delay just shows up because you didn't include those other physical variables that determine the future in your model. So it's like a simplification that leads then to that complication that you have to take the past into account. So here in this course, we're not really dealing with this. I just mentioned this as a clarification if you're confused about this notion that the present determines the future. So these are special extensions of that concept. Mathematicians think of discrete maps. So equations, iteration equations where time is discrete, also as dynamic systems for some good and deep reason. So here's an iteration equation where a variable x depends not on continuous time, but on some discrete time. And then if the something corresponding to a differential equation would be simply a map where the new future value is a function of the past value. And again, it would be just the immediate past, the last index n, not the whole history of previous indices. In some mathematical sense, there is a one-to-one relationship between discrete time, so-called maps, and continuous time dynamical systems, which we describe by differential equations. This goes back to Poincaré and others. So for instance, you can generate a discrete time dynamical system from every continuous time dynamical system using Poincaré's technique by making some sort of cut looking when a particular value is passed, for instance, through some plane. And in the reverse direction, you can do a lift, that is, you have a discrete time dynamical system, and then you can write down a continuous time dynamical system that has that discrete time dynamical system when you do the Poincaré cut on that. That's not unique. There are multiple ways you could do that. So that, is of interest to mathematicians. I'm going to recommend a book here, this book by Scheinerman, which is publicly available. It's free now. It's wonderful. Very, very good book. Really recommend that. Very elementary, if you don't know much, but it deals with both discrete and continuous time dynamical systems, always in alternating chapters. And if you look at that book, you will see that the discrete time dynamical systems are in some sense more complex. They have more complicated solutions. And that's really true. So for instance, even a single variable discrete time dynamical system can certainly have oscillations, and it also has even chaotic solutions, sensitive dependence on initial condition. While in continuous time dynamical systems, you need more variables to do with things like that. And we'll get an intuition in a moment why that might be the case when we look at numerical solution of differential equations, which actually make them maps, discrete time. But pragmatically, this also means don't study that. That's too complicated. We don't really need that. So in this book, I recommend you to really go for the continuous time versions. They might be more demanding in terms of computing derivatives and things like that, but conceptually they're actually easier in continuous time than in discrete time. Okay, now hinted at numerics already. Of course, in practice, we here in this community of using dynamical systems for robotics and using dynamical systems to understand neural networks, we're not actually ever solving differential equations analytically. That is ancient history for us. These are all nonlinear, complicated dynamical systems. We're all using them numerically. And I was just want to give you a brief hint at that. In practice, you're just using ready-made simulators, a hint at what's behind that. And essentially the idea is that shouldn't matter. The numerics should be done such that it doesn't really matter. And I'll just give you the core mathematical idea. The forward-Euler method is the conceptually easiest, even though it is terrible in terms of numerics. It's like the worst procedure you can do in a certain sense. I'll make clear in a moment. So in the forward-Euler, what you do is introduce discrete time. So you make it introduce an index. Simplest case, you have a time step delta t, so some constant, and so the discrete time steps are 1 times delta t, 2 times delta 3 times, and so on. And therefore, instead of a time varying function, now you have a long vector of x at the different time steps. And so instead of the differential equation, you have a map. So to see what the map is like is the derivative you can approximate by discrete change. So in the time step delta t, there would be a change delta x. So delta x, that's the change from one time step to the next time step. And therefore, if you have this equation, you replace the x dot by this, this divided by delta t. Put the delta t to the other side and add the xi, then you get xi plus 1 is equal xi, it comes from the delta, plus delta t times the function of x at that past value. So here the right-hand side is the past value plus the increment, right? So the increment is essentially proportional to the rate of change, and proportional to how large your time steps are. And so only the past value or the present value here show up on the right-hand side, so you can determine the future value here, and then you can insert that into the equation and determine the next value and so on. That's why we call it forward, because you can just iterate forward in time. You don't have to solve some equation to find the future value. There is a backward version of the Euler where you put the future value in here, and that's actually numerically better, but it requires solving this equation for the future value. So this is conceptually very easy. Also invite you maybe on a piece of paper to think through that and make sure that there's no mystery involved here. It's valid when you make delta t very small. It's valid. It's bad in the sense that you need to get a certain kind of precision. People really think about how the precision scales with the delta t, and this scales very badly. That is, to get some precision, you really need to make delta t very, very small. And on a computer, that means a lot of time steps to make a certain length of simulation. It's still useful, and we actually use it a lot in dynamical field theory. We use it in part because these equations we'll be using are very numerically not difficult. And it is sometimes useful in real-time systems when you have sensors and you cannot really do that many sensor readings. So you're sort of limited in computing these intermediate values that some other processes need. And actually for stochastic systems, it's an interesting topic that I'll cross over for now. So the more modern techniques are, even Runge-Kutta is a very, very old technique. That's a standard technique that scales much better. For instance, the standard Runge-Kutta scales with the fourth power of the step size. So if step size is very small, fourth power is a very small number. You can see that when you reduce delta t, the error goes down much more radically. And actually pretty much all the the procedures you have that people use have adaptive step size, which really means that the algorithms checks how much the result depends on the step size and reduces or increases the step size to the value at which the difference that it makes remains below some threshold that you define. And things like that are available online, like in Python. There are libraries for that. And in MATLAB, I'll show you here a little bit piece of MATLAB code that illustrates that. So first, let's look at this code. I hope that the font is sufficiently large for you to read. Could anybody type into the chat if that's readable?
Yes, absolutely, no problem.
Thank you, great. So this is an illustration. I put this simulator onto the web page, and if you're a student at RUP, and I think also at Dortmund, you can actually have access to MATLAB for free. So you can run this and play with that just to get some hands-on feeling. So this is not a simulator I recommend you using. It just clarifies what is contained in a simulator like that. So simulator in the sense of numerically solving the time course of a dynamic system. So here, the clear is just to wipe out any variable that you had in here. The model is really this equation I just showed you. So it has the parameter tau, which we can vary. There's a Moy strength here because this actually also does stochastics, but I'll not explain that here. And then here you can set the Euler step, so the time step, set currently to 0.01 in time units, right? The same units in which we measure tau. This final time sets the system up to integrate from 1, which would be the initial condition, to some final time. So that's how long the epoch is that you're going to simulate. And so time is actually a time series that has, depending on the time step, has enough time steps to reach that final time. And this is just the total number of steps computed from that vector, this array. That's the array notation in MATLAB that makes this vector here of time steps. And so variable is going to be the dynamical thing. I call that variable. Always recommend when you write code not to use things like x or x1, x2, but we use longer things where a typo will reveal to you that you didn't type what you meant to type. If you use x1 or x2 and then you typed x1 where you should have typed x2, then you will have trouble. So variable set up here to have a vector of as many entries as we'll have time steps, and we start with some initial value. This would be the initial value you can vary, and then the numerical integration is iterating in time. So an iteration index that starts from 2, because we'll assume the first one is given. Yeah, we have the first value already, to the number of time steps, and for every time step, we'll compute the right-hand side of the equation. So the right-hand side would be minus x divided, but it's minus 1 over tau times x. So minus xx is the variable at that just previous time step, right? If I'm at I time step, it was I time step minus 1. That's why we're starting at 2. So when we insert 2 here, then have 2 minus 1. That would be the initial condition divided by tau. And here's the update rule. The update rule, the other rule, is that the variable at the next time step is equal to the variable at the previous time step minus 1 plus the size of the time step times the right-hand side of the equation, which is here, this thing we just computed. Interesting note, when you have noise, rand n is a normally distributed random number with a noise strength, you actually have to multiply with the square root of the time step, a famously mistake a lot of people are making. So that's where the stochastics requires a little bit different treatment. But I'm not going to explain that here. And so here in this case, we're just plotting the solution as so the time on all these time steps and the variable at the same moments in time is plotted here. And actually, let me turn off noise because I didn't explain that. So if we run that, it will produce a figure. Oh, it takes so long. Ah, there we go. So here, this is time in discrete time steps, and that's the initial value here, and it just relaxes like that. So for instance, if I vary the initial value, it starts initially at 1. Your initial value is actually at 1, not at 0, because we have this time step 1. I could have started at 0, but that's what we did. And if I start at a slightly different initial value, for instance, let's say just start at 5, then I will get a plot that looks very much the same. Amazed how slow this is. It's maybe Zoom that makes my computer slow, or I'm sure. Or did I? No, is this the old one? Oh, I didn't. Apparently, I didn't press the button. So, no, what's going on? Did MATLAB crash here or what? Not a very good advertisement for. And it looks like it's still running here, or what's going on? I don't know. There we go. I don't know why it previously didn't run. So it looks very much the same, except because I have some serious slowing down here of my computer. Hopefully I'm not crashing soon. I shouldn't go too deep into these simulations. I don't want to create more problems. So you see here, it starts at 5 rather than at 1, right? And otherwise it looks the same. And I was going to vary steepness, but let's maybe not do that, because somehow this is really very taxing for my computer. Let's see what's going on here. Yeah, let's quit MATLAB, whatever that was. Let's not go there. The only thing I'll still want to show you this code, but I'll not run it. So let's have MATLAB start while I go back to the lecture. I want to show you this piece of code, or you can actually do this. Just look it up on the webpage, download this 2000, look at the other piece of code. Yeah, there it is. So the other piece of code is this would be the more realistic way you do that, by calling a ready-made adaptive step size function OD45, for instance, which takes as its argument the function, which is the right-hand side of the equation is this function f, the time interval, some initial value, and then that should be much more effective. Maybe you can dare to let that run. Yeah, see, it actually works. It's very, very steep here. It works much better. Let's make this, I think we had 10 in the previous case. So now you don't have to worry about the time step. 10. And now I must have had some typo in here. What is it? I know. I typed. Did I type this x here? I don't remember. Exponential. Oh, I know what happened. I somehow I must have done something wrong. I deleted something in this file. So let's not waste our time with that. Okay. So you can have a look at that, and that's a simpler, much more practical solution than this forward Euler that I wrote down. Good. So that's just basic dynamical systems. Yeah. Now what happens that here on my keyboard, sometimes the touchpad puts my cursor somewhere, and then suddenly I added something in the file that I didn't notice. Yeah. So the file on the web page isn't ruined, so that should work. So that's a very quick survey over dynamical systems as you learned in I don't know, high school or in the introductory courses that some of you have taken in math. Now, what we actually do in this course is something much more how should I say, more advanced or sort of simpler, depends on how you want to think about it. It's called the qualitative theory of dynamical systems from the point of view of mathematicians. They talk about it this way. It's a very good book that I recommend. It's a quite advanced book, but it's conceptually very clear. And if you just read the corresponding chapters, it's very useful. It's also available online now. I don't know if that's legal. I have the impression it is legal. Legally made available by the authors, actually, I think. I found it a really good book, but there are many books about that, and you have to find your own style. So this is not about solving a lot of the stuff that you learn when you learn this at the university is solving differential equations, all different kinds and different special cases and so on, analytically, I mean. Well, I'll tell you a little bit about what the qualitative theory of dynamical systems is. And that's really to characterize the ensemble of all solutions, sometimes called the flow of a dynamical system. And that's done typically by looking at special solutions that sort of constrain the flow, where you're then primarily interested in flows that are more or less equivalent to each other. It's actually the notion of topological equivalence, where you would say the ensemble of solutions up to maybe some stretching, sort of like in topology. You could maybe stretch them a little bit, deform them a little bit in the sense of continuous without breaking neighborhood relationships. And all of those you consider to be qualitatively the same. And then you're interested in differential equations or different cases for single differential equations in which there are qualitatively different kinds of solutions. And we'll see at the end of this lecture, you'll see that that's, if you think this way, that's very good for modeling, because what you do in modeling is that you have some ideas about the solutions you want, and you want to find the equation that has these kind of solutions. And the qualitative theory is lends itself really for modeling. So in this robotics world that we're looking at, you're confronted with that is you have certain kinds of constraints, what you want your robot to have as possible time courses of behavior, and then you try to find the equation that generates these kind of solutions. And similar, when we use this as a language for modeling neural systems, we might have some ideas of what these neural systems are supposed to have as functions, and then we're trying to write down a plausible neural model that could have that, and then compare that maybe to some neurophysiology that we may know. So that's why we're interested in this kind of theory. So the example I mentioned before actually makes it possible to illustrate that notion. So a very important concept is the concept of a fixed point, and this red curve was the example of a nonlinear dynamical systems I gave earlier, and already in the mental simulation I already hinted that if you start out here, you're going in this direction because you have a negative rate of change, so you will be decreasing negative rate of change and so on. The length of this velocity vector is, how deep it is here. That's the rate of change. And so when you're approaching this point, your length will decrease, right? The rate of change is so negative, but it is a smaller rate of change until here, it's a zero rate of change. So it will be staying here. So when you're exactly at this zero crossing of the dynamical system, your rate of change is zero, so you're not going to change anymore. And that is why we call that a fixed point. It's a solution of the dynamical system, but the solution is constant in time. And it's also one to which you are attracted. Someone raised his or her hand. Just speak up if you want.
I would like to know if this attractor point is just the same as the inflection point.
No, the inflection, here in this particular equation, there is in fact a change of curvature, and that's when my inflection point, right?
Exactly.
Yeah, this is true in this particular example, but there is actually nothing special about that. So there could be cases where there is inflection points are somewhere else. It doesn't really have much to do with what happens. For instance, you could have a case where it's going through this with all convex. Oops, sorry. Just shift this down a little bit. Then qualitatively nothing changes, but the inflection point will no longer be at that zero crossing. So it's just because I plotted something symmetrical here.
So attractor point always stays on the x-axis, right?
Yeah, the fixed point is always the intersection with the x-axis, because the fixed point is defined to be the point of zero rate of change. Now, fixed point means that zero point of change is zero rate of change. So it's the intersection with the x-axis. And zero rate of change means it's constant in time as a solution of the dynamical system. So if you start with that value, then your future is going to be zero change. So you're going to stay with that value. Yeah, so that's the notion of fixed point.
Good, thank you.
And so this is a special fixed point. It's a fixed point that is an attractor, namely to which neighboring initial conditions converge. So again, I argued for the right side. On left, positive values, you will increase until you're there. Right? So that's a fixed point that is stable. I'll define these more formally in a moment. And those are the fixed point attractors we'll be talking about. There are a lot of more ambitious or more advanced kinds of attractors. We'll talk about a limit cycle attractor a little bit in a little while, but in mathematics, there's most excitement is about much more complex attractors like strange attractors. Some of you might have heard about that, or quasi-periodic attractors, and those don't really play a role in this lecture. So again, maybe on a piece of paper, you should sort of go through that after lecture, maybe think about that. So see, it's no mystery here. It's really zero crossings means x dot is zero, f of x is zero, and that's what the fixed point is, right? Now, when I say it's an attractor, and we say then it's a stable fixed point, but that's jargon. Mathematically, that is what mathematicians call asymptotic stability. And I wrote down the mathematical definition somewhat informally. To do this mathematically, you have to be a little bit more precise. So a fixed point is asymptotically stable if solutions that start nearby converge to the fixed point. And that means any solution nearby. Nearby is this sort of environment argument. There is an environment so that of the fixed point, so that anywhere inside the environment you're converging. That environment could still be very small, but there is one. So it's this kind of epsilon delta kind of thinking that some of you might be familiar with from your math lectures. So all initial conditions, as long as they're close enough, will converge. That's what asymptotic stability is. And so this is intuitive notion of being attracted, right? When there is a other concept of stability that is really what mathematicians call stable, and that only requires that if you're nearby in the sense, then you stay nearby, but don't necessarily attract. And to make this more formal, you can imagine that you have to say something that, given the initial distance, you can give some bound. It doesn't go further than that bound. And so it's a little more complex to explain what that means to stay nearby. So we never really use that, except in this case of the billiard table, right? You can see the ball on the billiard table is not asymptotically stable, because if you shift it a little bit, it will not return to where it was before. It will just stay in the new solution. So it's stable in this more general sense. It will stay nearby, but it doesn't actually converge. And so we would say it's not an attractor, but it still has the stability probability. And the stability probability, this more general one, is important because the thing we are interested in is to be unstable. And unstable means not stable, but in this sense, in this more general sense, I mean, not staying nearby. That means that there are, so when you invert that, then that means there are some initial conditions that can be as close as you want, arbitrarily close to the fixed point. There are some initial conditions from which you will not stay nearby. That is, you will go beyond any bound. You will arbitrarily go arbitrarily far away. And we will encounter unstable fixed points. In fact, we'll be very much interested in playing with that, making fixed points that were stable, and I mean by that asymptotically stable, make them unstable, which means not just no longer converge, but even really diverge from a state. That's sort of a little bit more subtle notion of stability in there. So this is explained in the standard textbooks, nothing really very deep, but maybe not something you're entirely familiar with. The concept of asymptotic stability is the intuitive concept that many of you might have. Like if you drive a car stably, that means that if there's a little wind gust, you're going to return to your position on the lane, let's say. Not that you now remain close by being on the other lane and staying there. And also, of course, not that you fly off the road. That would be unstable. The first is asymptotic stable, the second would be just stable, and the third would be catastrophically unstable. Good. Now, I just want to make it a little bit more formal by talking about linearizations and eigenvalues and things like that. So here, this actually maybe harks back to the question Ali, I think was your name, just asked. Is the inflection point here right at the fixed point? And so I drew this red line by hand, so it's a little bit uneven. That's supposed to be a nonlinear dynamical system. It's not a straight line, but you can see that it isn't really very different from its linear approximation. The linear approximation was done here such that it is tangential and has the same fixed point. So I actually should say it has the same fixed point. So it goes through the same curve here as the red. I did this by hand, so you see both lines here. They should be really exactly on top of each other at the zero crossing. And then the slope at the zero crossing should be the same for the black and the red line. So that would be something that's tangential to the nonlinear dynamical system at that point. And the point I'm going to make is that this sort of linear approximation of the dynamics at an attractor can decide stability. And these kind of nonlinearities, where you would say in a sense qualitatively there's nothing really different between the linear and the nonlinear. That's a little quantitative difference, but not qualitative difference. Those would be not very important nonlinearities, sometimes called non-essential nonlinearities, for instance, in theoretical physics. And a lot of physics and engineering is based on treating nonlinearities that way. That is, you first approximate it linearly, and then you compute some corrections, sometimes called perturbation theory, where you're computing corrections to the linear behavior that just make some small quantitative difference. And we'll get in a little while to more essentially nonlinear systems that can really behave quite differently. So keep that in mind. So now let's briefly look just at linear systems. So in linear systems, the stability is really can be read off the slope. I already made this argument that a negative slope makes stability, right? This mental simulation on the right, negative rate of change, decreasing on the left, positive rate of change, increasing. For some mysterious reason, I switched to lambda as the variable here. I don't remember why. It's kind of hard to change these plots so quickly. So I have a couple of plots where it's lambda rather than x. Yeah, so negative slope makes it asymptotically stable. Positive slope makes it unstable, right? Positive slope, you would go have a little bit to, a little bit to right, you increase, growth, or a little bit to the left, you decrease, so you move away from fixed point. So if the slope is 0, that will be the table, right? The billiard ball table. Then it is actually stable in that mathematical sense, and physicists call this marginally stable, because you're not, so every point is a fixed point, right? So you would, if you shifted from the fixed point, you just stay there because it's another fixed point. So you stay close, but you're not converging. It's a very special case, right? Because a lot of things have to be true for this to be the case. So in multiple dimensions, this has to do with eigenvalues. I'm not going to explain that. I'm just connecting to knowledge that some of you might have. I know there's at least one electrical engineer here in the class. You know that you've all learned that in a multidimensional linear systems or vector values dynamical system that's linear, the stability of fixed points is computed from the real parts of the eigenvalues. If all real parts are negative, then you have of the eigenvalues of the linear system matrix. If they're all negative, then you have a stable state. If there's any real part that is positive, you have an unstable fixed point because there's one direction in which you're repelled. And if there's any eigenvalue where the real part is 0, then you have a marginal stability in that direction. So you need to be stable in all directions, right? Only then do you get really attraction. If there's a single direction in which you would diverge, then there's no guarantee that you're going to be attracted. So control theory is very much about fixed points. The set points of a control system are made fixed points that are asymptotically stable. That's how stability is used in control thinking, right? Just to connect that. Now, how about nonlinear systems? Linear stability theory essentially says that for the most part, the stability of a fixed point of a nonlinear system can be decided based on the linearization of the dynamic system around the fixed point. So you have the nonlinear system, you linearize it by computing this asymptotic thing that's essentially using a Taylor expansion for those of you who know that. So you just look at the right-hand side of the equation and make a Taylor expansion, and then the first term is the linearization, and from that compute the eigenvalues, and then really if all the eigenvalues are negative, in one dimension would be the negative slope, then you have stability, asymptotic stability, and if there's any real part that's positive, you have an unstable. Only difference is when the real part is 0, then you don't actually know. Then it's actually the nonlinearity that decides whether the fixed point is stable or not. These kind of fixed points are called non-hyperbolic for some reason. So here, illustrate that. Here, this would be, red line is the nonlinear dynamic system. This is a linear approximation here in black. That will be stable. Here, this will be unstable, right? Very clear. Now, this would be where the linear approximation has 0 slope, right? And you see that all kinds of things can happen, right? This would be a case where, again, plotted this by hand. This is supposed to be asymptotical here. So this would be a case where it would be unstable, right? Because it's here supposed to be positive here on the right. So it goes diverges. Here, the same linear approximation, but this one will be stable, right? And this one would sort of half stable. That is on one side, you're here on the right side, you would be attracted, but on the left side, you would be repelled. And here, this the other way around. So you see, in a non-dynamic system, when the slope goes to 0, then it depends. Then you have to really look at the non-linear dynamics. And this will be the kind of situation that will arise in bifurcations that we'll get at a moment, where we have to look at the details of the system to understand. It could be different cases then. Good. See, now it really accelerates. Now we'll do stuff that you're not so familiar with. So bifurcations. So bifurcations are change of stability. We're interested now in changing the differential equation. So when we're changing that, then we're talking about a whole family of dynamical systems. Usually we think of these families as being spanned by some parameters of the equation. If you write it mathematically, write it concretely as an equation, you have some numbers in there that you can vary. And we're always looking at differential equations where the dependence of the dynamics, the right-hand side of the equation, is smooth, right? So you don't do something where there's some jumps happen, a parameter that would have some non-continuous implications for the dynamical system. So we're always assuming that change is smooth in terms of the underlying forces. And we're then interested in something that is either smooth or not smooth in terms of the solutions. So roughly speaking, when the solutions also vary smoothly as an informal way of talking about continuous and maybe even differentiable dependence on this parameter. So whenever these solutions change smoothly, then we would say no qualitative change, because now you could think of the entire ensemble of the solutions as just having been a little bit deformed. Think of the solutions as functions that you plot on a rubber surface, and if you were to sort of pull on the rubber, that will be all just smooth deformations of that ensemble of solutions. If there's anything where neighboring points are mapped onto something else when you change the parameter, like you have to cut the rubber sheets and pull it back together in a different way, then that will be not smooth, and that's what will happen at bifurcations. And I'll make this concrete. Here's an example. I'm not writing down the equation for now. So the different shades of red are supposed to reflect different values of a parameter, and supposedly this is, I have plotted 3 levels, but if you vary that parameter continuously, the curves will be continuously deformed from the light red to the let's say the dark red. And you see this is here for the light red one, there are 3 fixed points here. This is an attractor, right? A fixed point with a negative slope. Here is a repeller, fixed point with a positive slope, unstable. And here's another attractor with a fixed point and a negative slope. And so what if I'm deform this vector field, this equation, so that this is pulled up, you see that what would happen is that this fixed point here would be moving, and that won't be moving as I change the parameter, right? Moving as I deform the equation. And these would be moving toward each other, and at some point they will collide and then lift up. There will be no more fixed point here. And see, there is going to be a qualitative change. Qualitative change in the sense that previously, the solutions that are here to the left of this repeller, they would all converge to this fixed point, and the solutions that are to the right, they would all converge to that fixed point. So there would be some kind of divergence as a function of initial condition. And then after that, all the solutions always go to this fixed point, and all of those go here to that fixed point. So if you have the ensemble of solutions for that latter regime, that would be all converging to one fixed point, and then you have the solutions of the previous regime, then there are some fixed points, some initial points left to the right of the repeller where they go in different directions. And these two you cannot transform into each other by just pulling on that rubber band. Here you really have to make a cut into the rubber band and make a qualitative difference between neighboring points. So that local thing here is called a bifurcation. This is actually a tangent bifurcation, and I think I have a plot for that. Maybe I don't have that. Yeah, here. Yeah, let's first discuss the. So I argued that we go through that by coming here from the bottom to the top, but I could also think of it arising in the opposite direction, right? The opposite direction would be that I'm starting out with this and pull this down, and then it would suddenly touch this here, build a new fixed point, and that would split into 2 different solutions. So there could be 2 ways we can look at that, as annihilation of a fixed point by colliding with the repeller or the spontaneous appearance of a fixed point. That's just the way in which this depends on the parameter value. First, do this here. So this is the so-called normal form of the tangent bifurcation. That is, this kind of qualitative change of the dynamical system where an attractor and a repeller collide and disappear, or they spontaneously arise out of nothing. The normal form is sort of the simplest equation that has that, but many other equations will also have it. Simplest in the sense, if you write the right-hand side of the equation as a Taylor series, it has the smallest number of terms and the lowest order terms. And the normal form, in fact, has only one state-dependent term, minus x squared, and a constant. And so that will be in the inverted parabola. And also flip that whole thing, can also be an upright parabola. The sign of this doesn't really matter, just it's a question of which attractor or repeller is on the left or on the right. So intuitively, this is an inverted parabola like this, and this here is the zero, the value where x is 0. So if alpha is positive, you have this kind of curve. Alpha is negative, you have that kind of curve. You can see when it's positive, you have two fixed points here, a stable one, there's an unstable one, and then below you don't have a fixed point. And so the fixed point, you can actually compute the fixed point. This could be a nice exercise, and I'll put this on the exercise sheet to compute that. And you'll see that the stable branch, the one here on the right, will converge to 0 when this alpha goes to 0. So right here, they are colliding, they are coincide. The unstable one is the one on the left, the negative values. And it turns out this goes like a square root of that parameter value. So you can sort of analyze everything in terms of that. And so the subtle little point I want to point at here is, remember the slope at the fixed point. That is what determines the stability. And you see the slope here is some number, and here it's flat, right? And so for the slope to go there, it must become flatter. And that's why the bifurcation is actually an instability, namely where the stability disappears, where this slope becomes less and less negative, ultimately is no longer negative, and that's when the point loses asymptotic stability, and a moment later the fixed point actually disappears. So bifurcations are actually associated with instabilities in the sense of change of the stability of the fixed point, ultimately qualitative, that is no longer being stable, and just before that becoming less stable. I didn't really talk about degrees of stability, but one can do that. And in the winter semester, actually, I'm making a lot more fuss about that, about degrees of stability. Good. What is interesting to us as designers is not so much these subtleties. When you do neural systems and analyze them, these measures of stability are very important because we actually can observe this stuff. As robotics designers, we're more interested in sort of classifying what can happen to then pick out of that dictionary of things that can happen the right thing. And that's where the Hopf theorem is very useful. It dates from the 1920s, and it proved that under certain conditions, there are only 4 kinds of things that can happen. So the conditions roughly are that there is a single eigenvalue that crosses the imaginary axis, meaning that its real part becomes changes sign, and there's some other technical conditions like so-called something about no special other complications, like other terms also being 0 at the same time. And there's also the complication that these eigenvalues in high-dimensional systems are complex, and therefore they arise in pairs of complex conjugate ones. So it can be actually one eigenvalue or a pair of complex conjugate. So you don't need to understand these complications. But there are only 4 things that can happen. It's kind of amazing. And the 4 things are really the tangent bifurcation. That's one thing that could happen. And then the other one is the transcritical one. The transcritical one, this is its normal form here. Instead of a constant, you have a linear term. And so it's a change from having this kind of parabola. And then as you can still think of, you're pulling down here on this end, put it down, and at the same time shift it to the right. So as you do that, so that this fixed point always stays. And you see in the critical point, it also just touches. And then you pull up the right leg and also shift left. so that this fixed point stays. And then now there's been a flip. Now this is the stable state, and that is the unstable state. So if you just look at zero, the zero actually changes stability from being previously stable to then being unstable. So if you look at a function of the bifurcation parameter, you have a stable and an unstable solution colliding, and as they collide, they exchange stability. So this is the stable state, and that is then the unstable state. Here they collide. It's kind of conceptually interesting because it shows that you can have a instability, because right here it will be unstable, right? The slope is zero. An instability in which there is no jump. It is something goes smoothly through that, but there is a moment when the stability is lost. And that is something that can really happen. And then the pitchfork is similar to the tangent, but with some symmetry constraints. So the normal form is this thing, the symmetry constraint. I drew this by hand, so the symmetry isn't quite so obvious. The symmetry is that when you mirror the equation, that you get the same, the function stays invariant under mirroring. And that makes, then you can't have the tangent, right? Because the tangent bifurcation, there's the attractor and the repeller. So if you mirror that, then the attractor becomes a repeller and vice versa. And here, this is invariant. And so what you need to do to go through that is you need to always have a second attractor here. So in this shape, you see here, if you change the sign of x, the equation will be the same because there is a change of sign here, and then this has the same sign. And so what will happen here is that this attractor is mapped onto this attractor, and there's always a repeller here. And the way then this goes through bifurcation is that you make the linear part, change the sign of the linear part. So when the linear part is negative, then you get a very clear attractor in the middle. When you make the linear part 0, then you get this third order equation, which still has an attractor here with slope 0. And then when alpha becomes positive, the linear part goes in this direction. Then around 0, where the linear part is dominant, you get a positive slope. But at larger values, you still have the nonlinear part determining that. So out here, you still have the the third order term making attractors. So it looks, if you look at the fixed points as a function of this parameter, it looks like a pitchfork. And this would be the handle of the fixed fork, Heugabel in German. So it would be, these would be the of the fork. These would be the two outer branches and the inner branch of the fork. And in this case, what happens is the bar, the 0 is the stable state. That will be this function, and then the outer ones are the stable ones, and the inner one is now unstable. But you can actually also always get the mirror image of that. If you invert time, then the stability inverse. So you could have a case where these are, all the red ones are unstable, and the blue one is the stable one. It's called sometimes supercritical and subcritical. Again, you don't need to need all the mathematical details, just need to know that one can classify these bifurcations in their not that many possibilities. You can really list the possibilities. The last one is the Hopf one, which we actually do use in this this course because we're looking at oscillations as well. So that actually requires some generalization of the things I just told you. And I use this opportunity to briefly explain where this notion of a vector field comes from. So if you have two dynamical variables, you cannot actually plot, x dot versus x, because you would have x1 dot, x2 dot, and you have, x1, x2, that would be a 4-dimensional plot. And of course, as you scale, it becomes hopeless anyway. But in 2 dimensions, very intuitive, what you're actually interested in is the so-called vector field. And the vector field means that in the original space, the state space, here 2-dimensional, x1, x2, the rate of change has the same dimensionality, right? You have a rate of change of x1 and a rate of change of x2, so f1, f2. So that also forms a vector of two numbers. And so you can draw it in the same plane, even though it has different units, right? It's per time. It's a rate of change. So here drawn as little vectors. So for every point in the plane, you have a vector such that the horizontal dimension of the vector is the rate of change of x1, and the vertical dimension is the rate of change of x2. And you can already see that it's that you can sort of see the solutions from this from this the structure of this vector field. And in fact, if you know a little bit of these kind of questions, you see that the definition of this is actually the tangent to the time courses. So if you know x1 as a function of time, x2 as a function of time, and you want to compute the tangent vector to these curves, the tangent vector would be this, x1, x2 dot. So if you think of the solutions, these vectors will be tangent to the solutions. And so by just following these vectors, you can see where it's going to go. Like from this initial condition, you're going to go to this point, which is a fixed point, where the length of these vectors is 0. And you can see the convergence pretty much visually in the vector field. Good. And so stability and so on can all be defined in these terms. So mathematically, any dynamic system can be written that way, right? If you have high dimensional spaces, you just can plot it this way. But mathematically, the rate of change is always a field in the state space and of the same dimension. You can sort of can think of it as a vector field mapping. So a mapping from the state space to this space of the same dimension. And that's what's called a vector field. And the analysis of these vector fields is really what dynamical qualitative theory of dynamical systems does. So the Hopf bifurcation requires that kind of picture, because what happens in the Hopf bifurcation is that there are complex eigenvalues. There's a pair of eigenvalues, and it gives rise to an oscillation. And the easiest way to look at that is not to do it in the original space. Here's the original space, x and y. So we need two-dimensional space to get oscillations. I already hinted at that. And the tangent bifurcation Hopf bifurcation occurs under such conditions when the eigenvalues are complex. And so what happens here is that it's a fixed point, and then at when the fixed point becomes unstable, in the turns blue, a limit cycle that is actually stable arises. Let me, I'll make this concrete by using polar coordinates in this plane. So x and y can introduce a radius and an angle in this x and y plane. R would be x1 squared plus x2 squared, the square root. And phi would be like, computed from the arc cosine, let's say, of y over x. That's a polar coordinates. And in polar coordinates, the normal form looks like this. In the radial direction, so the amplitude direction, you have the pitchfork. It's only for, I didn't plot the negative part because r is a positive number, right? The distance is only a positive number, the radius. And so that's from the pitchfork. So you either have an attractor at 0, or you have a repeller at 0 and an attractor at r. And in the polar direction, the angle, you have this trivial equation that phi dot is equal to a constant. So the rate of, that has a simple solution, it's a rate of change of is constant. So across phi, right? So then it will be, phi will be just increasing in time or decreasing if it's a negative constant in time. And now if you plug that back into the coordinate transform, the x will be r times sinus of omega of phi, and y will be cosinus of phi. Then you see, then you get an oscillation, right? It's of a certain amplitude. R will be the amplitude of that oscillation, and the oscillation will be sinus omega t, because phi dot equal omega means the solution is omega t. So again, I'll give you some chance to play with that math, but that's how oscillations come about. And so limit cycle oscillation, I didn't really find that. It's not a fixed point, even though actually in the Poincare section will be a fixed point. It's a periodic solution, and it's also stable in the sense that neighboring solutions are attracted to it. So to reduce the distance to that solution. One has to be a little bit careful about whether it has to, just the distance from that solution becomes 0. So it's not necessarily, so they could have some effects on the phase. So it's a question if the phase also converges. So I didn't want to go into these details, but intuitively it's very clear. It's a periodic solution that you're converging to from a neighborhood of that periodic solution. And we call that a stable limit cycle oscillator. And that is actually a picture that we'll be using later in the lecture to understand how timing is generated in the nervous system. We'll not go into the math of that in much detail. We're just talking about it conceptually. It will, in some models, we've actually used the Hopf bifurcation, but sometimes we use other equations that have the same qualitative dynamics, the same, just deformed from solutions of the Hopf bifurcation. Good. So I'll close by showing you how we use this to use dynamic systems as a language, essentially for modeling or for designing robot behaviors. And to do that, I point out the difference between forward and inverse dynamics. So forward dynamics is the sort of thing that you have learned at some point in your math course, where you're given an equation and then you have to determine its solution. In your courses, you sometimes learn how to do that analytically, and then I hinted that you could do this in numerical solutions. And then if you do qualitative theory of dynamical systems, you would try to characterize the ensemble of the solutions, for instance, by determining the fixed points or the limit cycles and determining their stability. And from that, you would know the flow, I would say, from any initial condition where I converge. Actually, the difficult part about that is to determine the so-called attractor basins of the set of initial conditions from which you converge. That is not always easy to actually really compute. In the one-dimensional examples we'll have, it's usually another fixed point, like a repeller, that is the boundary of the basins of attraction. But in high dimensions, this can be complex. So it's not always totally easy to make a quantitative analysis. So there are more general terms that one can think about, like the center manifold plays a really big role there. So it's just an illusion for those who've heard of those things. That's where these sort of things come in. So that's the forward dynamics. So the qualitative theory is the most advanced form of doing that, but just solving the equation, right? That's what you do. Like if you're a physicist, you take an equation that somebody has found out about and then just solve it. And some people do neuroscience this way, like they think that you would be able to write down the equation of a certain neural circuit based on some experimental determinations and based on the dynamics of membranes that were computed, let's say, in the dish in isolated neurons, and put that together and then solve that equation, maybe play with the parameters and solve the equation. Now, the inverse dynamics is that you know the solution or something about the solution, and you want to find the equation, an equation that has that solution. It's a question if that's unique, is there only one equation that does that? Not in general, because you can imagine that it depends on, maybe if you have a single solution, that's certainly not enough, because if you start somewhere else, the dynamical system will essentially say what the solution from any initial condition is, and you have only maybe a limited set of initial conditions on which you know something about the solution. So there will be certainly limitations in that way. And mathematically, you can get into really deep stuff. We're, of course, very pragmatic here, and usually just have some qualitative constraints, and that's how we're using qualitative theory of dynamical systems. So we will typically have not really literally have a solution, but have some kind of qualitative characterizations of solution. For instance, we would say we want certain kinds of attractors, and then maybe under some conditions, those conditions could be, for instance, sensory information that we'll have, and under other conditions, we want, for instance, some of those attractors to disappear or to become unstable, and then maybe new attractors to arise and so on. So we determine how the solutions change as conditions change. And what we then want is an equation that we can then implement on the robot and numerically solve on the robot so that it generates that solution. And if we link that solution then to the robot's motor system, the robot will do the behavior described by that solution. That's literally what I'll be doing next week when we talk about path generation in robots. And so we can use these bifurcations, the Hopf theorem and this qualitative analysis, the normal forms, to write down equations that have the desired qualitative solutions. So it's not only the attractors, but also the bifurcations as function of parameter. We could literally use the normal form. The normal form has the advantage that it's being the smallest polynomial on the right-hand side equation. It's not a very wrinkly equation, so it has not too many undesired other solutions. If you write a very complex polynomial as a model, then maybe you have the zero crossings that you want, but as you know, when a polynomial has high order, the number of possible zero crossings increases with the order of the polynomial, so it can have more and more complex fixed points and so on, and some of those might not be things that you want. So by reducing the number of terms in the equation, that really means smoothing the equation, not having a lot of wrinkles, you can make sure that it only has the fixed point that you want it to have, at least. It's not always in a proven way, but an empirically good approximation. We will see next week. Unfortunately, some of the systems we'll be looking at use angular variables, heading direction, and then the normal forms that I just showed you don't work because they are not on periodic spaces. They work on linear spaces, on R, real numbers, and the other ones work on S1, the circle. And therefore, the normal forms are with sinus and cosinus, and it's a little bit different from what I just showed you. But the spirit is the same. So we're using the normal form essentially to find a equation that is in an equivalence class that has these solutions, but it's also a very simple one, or it's one that has no other undesired properties. Yeah, that's as much as I wanted to present.